Hey, welcome back, you guys. We are going to talk about Newton's second law today. Let me make sure my pens are all set up. They look set up to me, more or less. Except now I bet they're not going to work, huh? Watch. I knew it every time. It's like you can't change the size. Alright, sorry. I almost deleted my frog. Anyway, we're going to talk about Newton's second law today. Newton's second law is probably one of, I'd put it like top 5 most important things you need to know for the whole class. Newton's second law is incredibly powerful, and this law gets used for almost everything. So it's gonna be super important that you get to know it and remember it and know how to use it. So let's go talk about it. All right, so let me tell you what Newton's law is, and then I'll tell you how to set it up and use it, right? So Newton's second law says that that the acceleration of an object is directly related to the net force acting on the object and inversely related to the object's mass. This is a really fancy way of writing an equation. If you read Newton's original 3 laws by Newton, from the primary source, they're almost unrecognizable. They're so Englishly written, and there's no equations anywhere there. It's so the opposite of what physics is to a lot of people, I think. And by a lot of people, I mean me. So what this little paragraph, or rather sentence, I guess, it looks like a paragraph because it's in big font, but what this sentence means is a formula. The formula is this. So the acceleration of an object is directly related to the net force, or the sum of all the forces, acting on the object, and inversely related to the object's mass. Make sense? Okay. So basically it says the bigger the net force, the bigger the acceleration, but the bigger the mass, the smaller the acceleration. Because when you make the bottom of a fraction bigger, the number gets smaller, right? Dividing by a bigger number makes stuff smaller. So this is Newton's law the way Newton described it. This is not the way that I think of Newton's law, and it's the way that you shouldn't think of it, because I'm biased and I'm your teacher and I get to tell you what to think. So what I think of as Newton's second law is this thing over here. So all you do is multiply mass on both sides, and then voila, F equals ma, and this is the formula that everyone knows and loves and cherishes, right? This is that formula's weird uncle who eats too many hot wings at family gatherings and then doesn't say goodbye to anyone except you. You feel me? But anyway, this is the important equation. This is the equation that's going to guide us in setting up problems and solving for stuff. And it's the one that's going to help you understand all those really lame jokes about Star Wars where people are like, may the mass times the acceleration be with you. It's because of this. So in an effort to prepare you to talk to Star Wars nerds for the rest of your life, we'll learn it this way. So here's Newton's second law. Newton's second law says the sum of forces is equal to the mass of the object times the acceleration of the object. All right. So there it is. We're going to take a slight detour before we dive into doing physics problems. And I know you're like, Mr. Barton, it's only 4.5 minutes into this video and you're already done with 2 slides. I'm a little worried you're not going to hit your 40-minute quota. Sometimes that's all right, kids. Sometimes we don't need to watch 40-minute videos. All right. So let's talk about something real quick. This is something we kind of skirted around. There's this phrase, directly proportional, in physics. And we should probably talk about it just so that if I name drop it later, You're not like, but what does that mean? You know what I mean? We need to have real formal definitions for things. So, what does directly proportional mean? Newton's second law is an example of a directly proportional equation, and it's kind of hard to tell you what that means in English words. So we're going to use math because that makes most things in physics easier. So here is Newton's second law. I've omitted the... Ooh, that's an ugly sigma. I've omitted the sigma because it's kind of just there for flavor, you know. But this is Newton's second law. This is our beloved displacement equation. This is directly proportional and this is not. What directly proportional means is that something is equal to something else that is a single term. Meaning this thing would not be directly proportional because it has 1, 2, 3 terms in it. Not directly proportional. Another way you can think about it is directly proportional is an equation that when you graph it, its y-intercept will always be 0. This thing, if I graph it, even if it's not the quadratic version, even if it's just our constant velocity displacement equation, it could be like this. This is not directly proportional. And that's really just the definition of it. But let's see what it means to be directly proportional and why this would not be directly proportional. Let's go ahead and double acceleration in both of these. So we'll double acceleration here and we'll double acceleration here. If I double this acceleration, my new force will be equal to 2 ma, which is 2 times the original equation. So if I double acceleration in this, I'm doubling the force. 2F equals 2 ma, right? Double the force. If I double acceleration here, x final equals a t squared. So this term got doubled because the 1/2 went away. But these two terms did not get doubled. So doubling acceleration in this equation doesn't have the effect of doubling the whole thing. It just doubles that one term. And now we can't, if I say let's double acceleration, how does the new final displacement compare to the original? It's probably bigger, but it's not double, right? And we can't really make any clear assertions about what it is. So, not directly proportional. Okay. I'll have you do some problems with this, and that'll probably clear things up a little bit. But in general, directly proportional means two things: linear and no y-intercept. In a directly proportional equation, if you double any of these, or you triple them, or you square them, or actually I take that back, let's not say square, but if you multiply or divide them by any constant, you will do the exact same thing to the other side of the equation, to the force. If you double the mass, you double the force required to have the same acceleration. If you double the acceleration that's happening to a mass, that means you applied twice as much force. If you cut the force in half, your acceleration will also be cut in half for the same mass. If you cut the force in half, you have to cut the mass in half to keep the same acceleration. So you can do a lot of really quick problems by knowing this is directly proportional. If we look at this, if I say you double the initial velocity, okay, but that doesn't double the final velocity, and it doesn't tell me I need half as much time, or, you know what I mean? You can't do as much quick math with this as you can with this, because this is directly proportional, is what I'm trying to get at here. So I'll throw a couple of problems like that on your homework, and you'll hate it, but it's fine. It's good for you. All right, let's go do some real problems. All reliable, my favorite problem. So It says a box is moving across a smooth table to the right and accelerating at a constant 2 meters per second squared. So they're telling us acceleration is 2 meters per second squared. If the mass is 3 kilograms, what is the net horizontal force acting on the box? Okay. So let's maybe draw a picture. I've got a box, and it's moving across a smooth table to the right, and it's accelerating. So it's getting faster. All right. This is a picture. Let's draw a force diagram. So for our box, of course, weight is acting on this, right? We've got weight going downwards. And because it's on a table, we've got the solid table pushing back up on it with a normal force. And we can say these are equal because those are the only things happening in the vertical direction. Now it says it's moving to the right and accelerating at 2 meters per second squared. That's all it says. Does it say what's pushing this or if it's being pushed? No. But because of Newton's second law, because our acceleration is 2 now, our forces cannot be balanced. If we add up our forces and we say, all right, this is it. There's just the normal force and the weight. These are balanced, and we know from Newton's first law that if they're balanced, this should equal 0. But it says right here acceleration is 2 and mass is 3, so this equals 6. That means our forces have to be unbalanced. So we can tell, even without the problem telling us, that there must be another force to the right because it's causing this acceleration. And we want to know, what is this force? So we can just call it force applied. This might be someone pushing it, like there could be a hand here, right? And it's pushing on this. Or there could be like a rope, and someone could be pulling it. There's a bunch of ways to make stuff move. But just by them telling us that it is accelerating, we know there must be this force that they don't really describe in the problem because of Newton's second law. So if we want to solve for that force, the sum of forces in the x direction are this force applied and we could even, let's throw a friction on there. Maybe there is friction. Actually, there can't be friction. A smooth table. I take it back. Okay. So the only force in the x direction is force applied. Okay, so the sum of forces in the x direction equal the force applied equals the mass times the acceleration, which we said was 6. So this mysterious force, what is the net horizontal force acting on the box? The net force, which is equal to the force applied, is 6 newtons. Cool. There you go. Easy. All right, let's do one where we've got a couple more forces and we have like real definitive stuff for them. But yeah. Now we have a rough table. Now we can friction. So a box is sliding to the right on a table and is gradually slowing down. The box is moving at 1 meter per second to the right initially and stops after 4 seconds. What is the average force of friction during the 4 seconds? So we've got the same problem here. We've got our box. It's sliding to the right on the table at 1 meter per second at the beginning. But this thing is going to slow down and then eventually stop over here. And ignore the change in shape in this big lump on this side. So let's go ahead and draw our force diagram. So of course we're going to have our normal force and our weight. And those are equal because they're the only two forces in the y direction. Now, because our object is moving to the right, we know friction opposes the way you're trying to go. If I try and push a table to the right, Friction is going to push against me to try and keep that from happening, so it'll go left. So because our object is sliding to the right, we have to have friction to the left. Now that they've really nailed down, here's friction, it's going to slow down and stop, and they don't tell us anything about any other pushing force, we can go ahead and just assume there's not a force applied. If they wanted it to be there, they'd have to give us a name for it. They should say it's there if they want it to be there. Otherwise, it's within our rights to say, that's not there. So let's go ahead and set up our sum of forces equation. So our sum of forces in the x direction are equal to just negative friction. And I'm making it negative because I like to say to the right is positive and up is positive. So left, I'm going to make that thing negative. All right. Equals the mass of the object. Oh no, did I not give us a mass? What do you guys want the mass to be? Let's make it 4 kilograms. Is mass times acceleration. Okay. So I didn't give you the mass, but we'll say the mass is 4 kilograms. Okay. We still don't know the acceleration, so we're going to have to calculate that. Let's look at the information that's related to acceleration. Acceleration is change in velocity over change in time. We have a starting velocity, we have an ending velocity, and we have an amount of time. So let's go ahead and solve for it. So velocity change is final minus initial. We end at 0, we start at 1, divided by the change in time. How much time did that take? 4 seconds? So acceleration is negative 0.25 meters per second squared. So we're losing 0.25 meters per second every second from our speed. All right, that's our acceleration. Now we should be able to solve this problem pretty easy. So our mass is 4. Our acceleration is negative 0.25. Our force is negative friction. 4 times negative 0.25 is negative 1 equals negative friction. Negatives cancel. So friction is 1 Newton. And this negative is telling us that it was to the left. So to the left. Or we could just put a negative on there. Either way. Okay, so friction is going to be 1 Newton. There we go. Pretty cool. All right, I've got one more, and this one I promise has more than one force in it, so we can really get the spice of Newton's second law. And then you'll have some problems to really cut your teeth on, and you'll love it. Don't worry. So, Old Reliable's girlfriend, as I like to call this problem. We have a 3 kilogram box being dragged across a rough surface, so that's kind of implying friction to me, by a rope. Okay. The rope has a tension of 5 newtons. And they're going to measure that with a force gauge attached to one end. The whole system is gradually accelerating at half a meter per second squared in the direction the rope is pulling on the box. Find the force of friction. So let's look at a picture first. Let's see. Let's make this a little more compact, right? So you're over here, and you've got a rope, and you're pulling on this thing. There's your grubby mitt. So you're pulling on this thing, having a great time. Too bad you can't see because your head's transparent. But you're pulling on this rope, and you've got like a little force gauge here. Whoop. Force gauge, and that thing's going to tell you how hard you're pulling on the rope, and it tells you 5 newtons. This table is like one of the school tables, so it's covered in dirt and drool from sleeping students, and it's going to hold it back a little bit. So it's not going to accelerate with the full force of this rope. It's going to accelerate a little less just because of friction. So our goal here is knowing how hard we're pulling, 5 newtons, knowing the acceleration and the mass of the box, we want to figure out what is friction. So we're going to draw a force diagram to, look at a nicer picture of what's going on here. Let's balance our table. And then we'll use a sum of forces equation to try and figure that out. So for our forces, we have the weight. We have the normal force. We have the force of tension being rope forces. And then we have the force of friction. Because we know we're accelerating, the force of friction has to be a little bit smaller than the tension force. Because if they balanced, then we'd be using Newton's first law, and our sum of forces would equal 0 rather than ma. So this is our force diagram. Let's go ahead and write our sum of forces equation. So sum of forces in the x direction. So we're ignoring weight and normal force because those are boring and they're just balancing, So in the x direction, let's make to the right positive. So we have tension minus friction equals mass times acceleration. We're saying mass times acceleration here instead of 0 because we use 0 when acceleration is 0 because 0 times anything is 0. But here it's 0.5 meters per second squared. So let's go ahead and plug in what we know, and then we're going to solve for the missing force that we don't know. So our mass is 3 kilograms. Our acceleration is 0.5. Our tension is 5 newtons minus friction. So we have 5 minus F equals 1.5. Now we're going to subtract 5. So we have negative F equals negative 3.5. So friction is 3.5 newtons. And then because it's to the left, we would say it's negative. Ta-da! There you go. Now we know friction. It wasn't that fun. Okay. And I think we're going to try and keep it about that difficult for right now. Eventually what we're going to do is we're going to not just ignore the y direction. And there's going to be some dependency here between those two things. But I'm trying to just make sure you guys are comfortable with the whole force diagram thing and the sum of forces thing. So, yeah, I think that should be all right. Okay, if you have any questions, make sure you ask me in the WebEx. And until next time, have a wonderful day.